In this video, we're going to talk about some basic topology of the complex plane. We're going to start off with what's the definition of a topology. So here's what we do. Take a subcollection T of the power set of the complex numbers. So in other words, let's say I took a bunch of subsets of the complex numbers. But they have to satisfy the following things in order to be called a topology. So here's what T, my collection of subsets of complex numbers, has to satisfy. Number one, the empty set and the whole set of complex numbers have to be elements of T. So those have to be two subsets that I pick to be in T. Number two, if U1 through Un are elements of T, then their intersection has to be in T as well. Another way to say that is that T is closed under intersections of finitely many things from T. Number three, if U1, U2, etc., notice how I'm allowing this list to possibly be infinite. If I have a bunch of things from T, finite or infinite, then their union have to be in T as well. And so T has to be closed under unions of arbitrarily many elements, finite or infinite. So if my subcollection, the way that I chose my subsets of complex numbers, if I satisfy these three conditions here, then what we're going to say is T is a topology. So that's what it means for T to be a topology. And these things that are elements of T, they're special in some way, right? Like, oh, these are somehow special subsets, right? We're going to call those elements of T open. So open sets are just what are the things that are in the topology that you're talking about. Now, there could be many topologies that people could put on the set of complex numbers. There's lots of ways to pick subsets of complex numbers and throw them together and satisfy number 1 through 3 here. We're going to focus on one topology on the complex numbers, and it's typically referred to as the usual one. And it's defined by way of the distance function. Remember, we measured the distance between two complex numbers z and w by taking the absolute value of their difference. So here's some notation we want to get used to. And what we're going to actually start off doing is by defining some special subsets of the complex plane. So the first one, CZR with the brackets there, that's going to denote the set of all complex numbers w whose distance from z is exactly r, where r is some positive real number here. And now if you think about that, I want all the complex numbers whose distance from z is r. That's a circle. That's a circle centered at z of radius r. So CZR is just a shorthand notation for the circle centered at z. So that first slot there, z is the center, and r is just the radius. The next piece of notation we're going to run into is DZR, and that refers to all complex numbers w whose distance from z is less than r. I almost said at most, but I don't want to be equal to r, so it's less than r. And what is that then in a picture? That would be all the points that are inside of that circle. And so we're going to refer to that as you see, I'll zoom in a little bit on the bottom here, we're going to refer to DZR as an open disk of radius r centered at z. And just notice it does not include the actual circle CZR, so it doesn't include that. That's what my dotted lines are trying to indicate. Over to the side, I say sometimes DZR is referred to as an open neighborhood of Z. That word neighborhood might come up later in these videos, or if you take a topology class, you'll typically refer to these kind of special open sets as neighborhoods. Okay, so we're going to continue. We're going to name some points of these two special subsets of the complex plane, of this disk. And so let's talk about naming, some vocabulary for naming points that are in this disk. So the first picture here, I would say W like this is an interior point of the disk, right? It's literally inside the disk. That's all I mean right now. And otherwise, in my other picture to the right, I would say that W is a boundary point of the disk. And so we're going to come back to these terms interior point and boundary point a little bit later on. But again, for now, I'm only telling you about these two special subsets of a circle and a disk, and we want to remember this vocabulary of what an interior point at its heart kind of is and what a boundary point is. And in both pictures, each W that I drew for you in the pink and in the orange, either one of those we're going to call an accumulation point. And just how I want you to think about that right now is that no matter how close I get to W, I can always find points from the green that are next to W. All right, so this distance function, I just kind of showed you how we use the distance function in order to define what open disks are. And now what we're going to do is we're going to use these open disks in order to define what is the usual topology on the complex numbers. So in other words, now I'm going to use what an open disk is. I'm going to use that as sort of a tool in order to define what is an open set. So just more generally, maybe it doesn't have a disk kind of shape. So we're going to say that any subset U of the complex plane is open if the following happens. For each element of U, there exists, somehow an H got deleted, there exists a real number that's positive, R, such that the disk centered at Z of radius R is contained in U. Now I've got a picture for you. I'm saying that U is open, so remember, like U itself is not a disk, right? But what does it mean for U to be open? That means that we should be able to, for any point in U, we should be able to find a disk centered at Z, and that disk has to be completely contained inside of U. So that is what it means for a set to be open. And so the collection T of all such U, so if I think about, all right, I'm going to take all subsets U of the complex plane that satisfy this, that contain a disk around any of its points. If I throw those together into a bag and call it T, that bag is a topology, and it's called the usual topology. And somehow Y got deleted. The usual topology on C. And you could check that this family T satisfies 1 through 3 in the definition of a topology above, and of course if you take a topology class, you probably will check that. You should check that yourself. So in other words, again, we're going to say that a subset U of the complex plane is open if each point in U is the center of some open disk or ball in U. Ball is another term that you might use more often in a topology class. I'll try to stick to disk. So what we're going to do next is we're going to look at extending our vocabulary that we use to define points in and on the disks. We're going to use that vocabulary to try to describe points that are in any set. And so as our model for any set, I drew this goofy looking G over here, and G has like one little point that's outside of it. It's outside the squiggles. So G is all that stuff, and then the little point to the side too. And so what we're going to talk about is trying to label and describe some of these points in G. So number one, we're going to say that a point of G is an interior point if some open disk centered at Z is contained in G. And so over to the side here, I've drawn you a picture of what a typical interior point might look like. And again, I'm just saying you should be able to find some disk that fits inside, that's centered at Z and that fits inside of G. So that Z would be an interior point if it's the center of some disk that fits inside of G. Now, yeah, you could make a smaller disk, like there could be lots of them. So this is where you need to keep your quantifiers in mind. We're just saying we need to find some disk that's centered at Z and fits inside. Number two, we're going to say a complex number. Notice how I'm not saying that Z is in G. I'm saying Z is in the complex numbers. We're going to say that it's a boundary point of G if every single open disk centered at Z has a point of G and a point that's not in G. And here's some notation. This partial D, it looks like a partial derivative. I'll just say partial D. So partial dg, that's the notation for the boundary of G. And so over to the side, I've got a picture for you. And if you allow me to zoom in a little bit, let me try to emphasize what's going on in the definition again. I've drawn that point Z for you right there. And now here's what I want you to think. No matter how small of a disk I make around Z, you will always be able to find a point in the yellow that's in G and a point in the black that's outside of G. So I want you to think about that and convince yourself that no matter how small you make that disk, you will always be able to find a point in G and not in G. That is what it means for Z to be a boundary point. And so that's how we're going to mathematically describe what like the boundary of a shape is. And so again, we're going to talk about all the boundary points together. That set is denoted by this partial derivative notation, dg. Number three, we're going to say that a complex number, and again, notice how I'm not saying Z is an element of G. We're going to say it's an accumulation point of G, though, if every open disk centered at Z contains a point of G that's different from Z. Over to the side, I've drawn you two pictures here, and I've drawn you two numbers Z that are good accumulation points of G. And so what do I want you to think about from the definition again? No matter how small I make either one of those two disks, you can always find a point from the yellow that's inside the disk, and it's different from the purple point Z itself. So that's what I mean by for every open disk, so no matter how small you make it around Z, you'll always be able to find other points in the yellow that are inside the disk as well. So that's what it means to be an accumulation point. Another name for an accumulation point you might hear is a limit point. All right, the last thing as far as these points go, describing these points, we're going to say that an element of G is an isolated point of G if some open disk centered at Z contains no other points of G. In other words, you can kind of isolate it from the rest of G. And of course, this is where finally the little dot outside of G comes into play. So remember I told you that little dot, I defined it to be part of G, and so he's an isolated point of G because I could put some disk around it that separates it from G. So again, keep your quantifiers in mind. You just have to be able to find a disk that separates it from G. Whereas with accumulation points and with boundary points, that's when you're thinking about every disk has to have that property in the definition. So keeping those quantifiers in mind is important. What we're going to move on to is we're going to try to expand and extend our vocabulary that we use to define the points that are in and on the sets to describe the actual sets themselves. And so we're going to say that G is an open set if all of its points are interior points. And we'll say that G is a closed set if G contains its boundary. And so in a topology class, you might hear some other characterizations of what it means to be closed or even what it means to be open. But these are the two ways that we're going to think about open and closed for the usual topology of the complex numbers. And so here's a note though. Some subsets of the complex numbers are neither open nor closed. So I'm not trying to say that any subset of the complex numbers is one or the other. I'm just saying that these are two terms that we might use to describe some subsets of the complex plane. So again, it's possible some could be neither open nor closed. And just in case you're wondering, in the usual topology, the only sets that are both open and closed are the empty set and the whole set itself. So let me give you an example. I claim that this set G, which consists of all complex numbers such that 1 is less than the absolute value of Z minus 1 plus I, which is less than 2, I claim that this is an open set. And maybe we haven't seen what on earth this set is before, but over here, it's just an annulus, so it's kind of like a donut. And it's centered at the complex number 1 minus I. And you might take a look here inside of there just to convince yourself why you should be centered at 1 minus I. But you want to think of that as this is the distance from Z to some number W, and to get that W to work out, it has to be 1 minus I. And so 1 minus I is just the center of that annulus, and I've drawn it down there for you here. And now let's talk about why should this be open. So let's look at the proof. So we finally get to do a proof in one of these videos. So let's say you took any point that's inside the annulus, that's in G. So there's my Z right there. And here's what we're thinking. I need to show it's open, right? I need to show you that for this arbitrary point that I plopped in here, we should be able to find some disk centered at Z that fits inside the annulus. This still stays in the red. And so here's what we're going to do. We're going to look at W1, which is maybe the closest point to Z that's on the inner circle of radius 1. And then, so let's talk about that point W1. So it's on the inner circle centered at 1 minus I of radius 1, such that though, again, it's closest to Z. And so another way to say that is that the distance from Z to W1 is less than or equal to the distance from Z to W for all other W that are on the circle of radius 1. So it's closest to Z for all those other points that are on that inner circle. Now what I'm going to do is I'm going to do the same kind of thing. Let's think about W2. Let's look at the point on the outer circle that's closest to Z. And so again, in our math words, how do we talk about that? W2 is going to be the point on the outer circle, C 1 minus I, comma 2, such that, again, what do I mean by it's closest to Z? I'm saying that the distance from Z to W2, so that's absolute value of Z minus W2, is less than or equal to Z minus W for all other W that are on that outer circle there. And now what we're going to do is we're just going to measure like exactly how far is it from Z to W1 and exactly how far is it from Z to W2. And what we ought to do is just pick the smaller of those two real numbers. I'm using this notation here. Use R, choose R to be the minimum of those two real numbers. Again, maybe minimum or infimum if you use that more often. I'm just saying pick the smaller of the two and let's let that be our radius. Because then if you think about it, if you drew a little disk of whatever the smaller of those two distances is around Z, you're going to fit exactly inside of that red, or only inside the red. And so in other words, that disk of that radius R should be contained in G. And so we just showed that any point Z is the center of some disk that stays inside of our set, so of course G is open. All right, so we've got some more definitions to run through here about, again, describing subsets of the complex plane. So we're going to say that a subset G of the complex numbers is bounded if there exists some other complex number Z and some positive real number R, such that G is contained in the disk centered at Z of radius R. So in other words, we're going to say a set is bounded if it fits inside of some disk. we're going to say that two sets, G and G prime, so two subsets of the complex numbers are separated if there exist two open sets, U and V, of the complex numbers, such that the following two things happen. So number one, those two open sets, U and V, their intersection is empty. And remember, a fast way to say that is to say that U and V are disjoint. And number two, G has to be contained in U, while G prime is contained in the other set, V. And so that's kind of the separating part there. So the first one says U and V themselves are kind of separated, but then the next part says is that G lives in the basket U and that G prime lives in the basket V. And I've just got a picture here with an example. So I just drew two blobs here in yellow, and one is G, the lower one's G, and the upper one is G prime. And then I'm showing you that I could separate them. So I just need to find you two open sets that do it. There are lots of possibilities for what the open sets are that you choose to separate these two. I just picked these two here, where I looked at in my picture, if I'm assuming my axes are labeled correctly here, U is the bottom blue part, bottom left. And so how you would describe that little portion of the plane, I'm saying the real part of Z is, say, less than -1, while the imaginary part of Z is less than 1. So I'm below that horizontal line at 1. That's the imaginary part, remember? And then G prime is contained in V up here. And so V is the upper blue part, which if you were to describe it, again, assuming that my picture is all labeled okay, the upper blue part would be all complex numbers whose real part is bigger than -1. You're to the right of that vertical dotted line. And then the imaginary part of Z is bigger than 1. So you're above that horizontal line. So that would be V. And so, again, that is what it means for G and G prime to be separated. The next thing I want to tell you about is what's it mean for a set of complex numbers to be connected. And it's connected if G is not the union of any two non-empty separated sets. So maybe another way to think about that is like, there's one piece of G. So G, if I was to think about G and G prime, if I was to mash those together and think about it as one set, take the union of those, then that would not be a connected set. Or if you allow me to scroll back up here, if I was to think about this set G, it's got that little point outside, so that would not be a connected set either. Whereas, if you take this annulus, an annulus is a connected set. It's not possible for me to disconnect the reds somehow by two non-empty separated sets. And similarly, this little blob G that I drew here, that blob would be a connected set. All right, so then just some other examples though. A disk is always going to be connected, and the whole complex plane itself is connected. And I need this definition of what connected is in order to tell you about what is a domain. So a subset G of the complex numbers is a domain if G is 1, open, and 2, connected. And so a lot of what we're going to go into when we start talking about functions that are defined for complex numbers, we need to talk about domains. And so yeah, you'll see the importance later on in later videos. But let's look at some examples about what domains are and maybe about what domains aren't. So the first example, again, if you take any disk centered at some complex number Z of some radius, right, any disk you take is always going to be a domain. On the other hand, let's look at like a more fun example. Let's say P is the set of all complex numbers x plus ix squared, where x is a real number, and that's not a domain. And that's just a funny way for me to describe, my favorite parabola, y equals x squared. If you think about it, right, the imaginary part is the real part squared. It's the same thing as y equals x squared. Anyway, let's talk about why it's not a domain. And it's not a domain, and if I'm thinking, what's it mean to be a domain? It looks connected, like it's not separated, right? So it must not be open. And so, of course, that's what we're going to try to show. So we're going to try to show that P is not a domain because it's not open. And just so we get our feet wet with how, again, these arguments kind of go, what's one way to do it? If I was to take a point Z that is on the parabola, then the idea here is that there's no real number r greater than 0, such that a disk centered at Z of radius r is completely contained inside the parabola. And so let's talk through a little proof of, let's look at a picture to kind of help us go through a proof of what I'm trying to say here. And by the way, there are lots of ways to try to show a set's not open. If you're familiar with topology, maybe you try to show it's, that it's closed. Maybe you know that this set's closed, or maybe you try to show that its complement is open, so this thing can't be open. Anyway, so what are we going to try to do though? So let's say I pick some point Z, so its coordinates, are x and x squared, or x plus ix squared, if you want to think of it that way. And I'm just going to plop any disk of radius r around Z here. And so here's what I'll do. Obviously in the picture there are points that are in the black, that are not on the blue parabola. And I just want to describe one of them to you. If I can find one point that's in the disk that's not on the parabola, I win. Then that says the disk is not contained in the parabola. All right, so then that's one way to do it. Why don't I keep the y coordinate the same, but I'm just going to move to the left r over 2 units, right? I'm just going to move a little bit to the left, about halfway there. And I'm going to think about that point. So that point is in the disk, but it's clearly not on the parabola anymore. All right, so then that's going to be the motivation for what my proof is. So to see that this disk is not a subset of the parabola, consider this complex number whose real part is x minus r over 2 and whose imaginary part is x squared. And again, over here, that's just shifted to the left, r over 2 units. So that's in the disk for sure. But if you think about it and if you look, that can't be on the parabola. And how do I know it's not on the parabola? The parabola has this special relationship, right? That the imaginary part has to be the real part squared. But x minus r over 2 quantity squared is not the same thing as x squared.